So today I'm going to talk about the photomodulation of neuronal activity in our body by organic polymer-based biointerfaces. So basically, and I'm working in innovative device and interface laboratory in the Department of Electrical and Electronics Engineering. This lab we prefer to call Idea Lab, and this university. So before I'm going to tell you something about the university and what we work in our lab. So yeah, so this Koch University is placed at the junction of Asian continent and European continent, and it is on the European part of the country. So you can see that there are a lot of beautiful pictures from the Istanbul, and it is known for more for tourist business. And there are 2-3 institutes which are doing work especially closely related to the European Research Council, and one of them is the Koch University where I work. In our lab, in Idea Lab, we work on a variety of possible solutions for some fundamental devices. So it covers starting from the material synthesis and especially colloidal inorganic nanocrystals like indium phosphide, zinc sulfide, core cell structure, etc. And using those colloidal quantum dots, we work on light emitting diodes. There are work also related to the green luminescent solar concentrators, and which involves proteins and nanocrystals. We work on biointegrated lasers and waveguides as well. And like 3 to 4 years before, we started working on neural interfaces as well. And we are the group of like 15 people from the different background, from material science to physics, chemistry, and then biology as well. So with this introduction, I would like to share my outline of this presentation, in which I'm going to talk about the motivation about the work, and we will talk about briefly some fundamental concepts so that everyone can understand what we are trying to do. And next two parts will be related to my work, which is important for artificial retinal implants. So if we talk about the motivation, this neural prosthesis is a very important part nowadays because of many diseases which is related to the visual prosthetics, auditory prosthetics, and prosthetics for pain relief, motor prosthetics, and some of the important diseases like Alzheimer and some other diseases which makes people blind because of the photoreceptors loss. So I'm going to talk specifically about the visual prosthetics, which is related to the retinal prosthesis devices. So if you see, this is a global disease basically, and this is in this retinal degeneration, which is global disease nowadays. In 2014, Lancet Global Health has projected that more than 30 million people in the world are blind because of the loss of photoreceptors, and those photoreceptors are responsible for the vision. And there are two types of diseases, which one is related to the aging population and other is related to the genetic population. So it is because of the some of the people are blind because of the genetic disease. So what we can consider here, like with the schematic, that this is our structure of our eye, and where the photoreceptors lie between the pigment epithelium and bipolar neuron. So these photoreceptors basically they are two types. One is rod cell and another is cone cell. So the rod cells are important for low intensity vision, and the cone cells are important for color vision. So these rod cell and cone cells, somehow with the age, they get deteriorate, and some people are genetically affected with this, and they don't have the photoreceptors. But these bipolar neurons are active and they don't have any photoreceptor to connect and send the signal to the brain. So what happens, like what we do, we place a artificial photoreceptor, which is our semiconductor device. And this artificial photoreceptor, we replace all the bad photoreceptors with this artificial photoreceptor, and then this start doing work and sending the signal to the brain. So this is our idea to get the to restore the vision using the semiconductor devices. So I hope this is having like enough motivation we are having for working in this field. And in fact, there is a projection in 2035 there will be 130 to 140 million people in the world will be blind because of this disease. So in this field, the people have started working since 19th century, but the relevant developments happened during 2000 when optogenetics comes into picture, and they found that by modifying the genes, they can restore the vision. But due to the modification of genes, it involves a lot of side effects, and it now the people are thinking that it is not going to succeed. So there are other two research which is related to the Argus 2 and Alpha IMS. These two are the clinically approved devices. But if you can see that these two devices have cumbersome electronics and multiple wirings, glasses. So it is so big and so clumsy that, and it is not feasible to put it in front of eye and have the vision. So and it becomes and it is too expensive as well, so it is not for mass population as. So they started stopped the working on these two devices as well, and the research in this field has been opened up again, and it is very important. It is at very initial stage how to get the cheaper devices, and which is more relevant, more flexible to put into the eye to get the vision. So there are third category which now we are working, and it started like getting focus from the 2010. It is the photoactive surfaces, and these photoactive surfaces are taken from the solar cell business. So from the photoactive surfaces, they are having simple fabrication, they are low cost, and they don't need power supply. The power supply is done by the solar light. So and it is good for our eye as well, because we are having vision because of solar light or any light. So with this concept, what I'm going to introduce that since it is the material conference, so we need to understand what kind of materials can be utilized for these kind of applications, and which one is good, which one is what are the pros and cons with the materials. So there are two type of, basically there are two categories. One is inorganic semiconductors and another is organic semiconductors. So I hope everybody knows that the the solar cells are made by these two type of semiconductors nowadays. So these inorganic semiconductors have starting from silicon based to the nanocrystals, quantum dots, and all of it can be used for the photostimulation. However, the organic semiconductors have another advantage over an advantage is unique advantage over inorganic semiconductors, that is their flexibility. These are the polymers, and these polymers have elasticity in the range of 1K to 10K. However, inorganic semiconductors have elasticity in the range of 1 mega to 1 giga. So this is so hard materials, and these are the flexible materials which is having same elasticity, which is equivalent to the our biological interfaces. So in this way, people have started with the inorganic semiconductors, but now they are moving towards the organic semiconductors, and to prepare these kind of organic devices which is suitable for the eye application. There are some essential points we need to know before going into this work, and what are the safe procedures for neural stimulation. So basically we are trying to stimulate the neurons using these semiconductor devices, which is placed in place of photoreceptors. So uh, these uh, these criteria are like threefold, you can say. which is fundamental. First is that it should be biocompatible. So as I said that organic molecules and organic polymers are more biocompatible towards the biological interfaces. Another point is that it should be without wire. There should not be any wire, and there should not be any implanted electronics, because it is going to deteriorate under the electrolyte environment of the body. So it should be wireless. Third component is the capacitive photostimulation, which is very important. And in this capacitive photostimulation, I will tell you in a little bit in detail in further slides. But right now, I would like to introduce few points like capacitive photostimulation mechanism. In this capacitive mechanism, we know that it is driven by the displacement current, and that displacement current associated to the charging and discharging of the electrode electrolyte double layer. So this way, what we see that there is no permanent displacement of currents, but there is a redistribution of charge species in the electrolyte, which is important. We don't want any permanent damage. And on the other hand, Faradaic mechanism. So this Faradaic mechanism is having the transfer of electron across the electrode-electrolyte interface, in which it involves oxidation and reduction of the some of the species in electrolyte, because of which there are irreversible reaction, and it can damage permanently few of the functions of the eye. So it is not suitable for this kind of devices. So we are going to focus on the capacity mechanism of the devices. This is another challenge in this field. So as we understand that capacity charge delivery is very important, very critical for this. So next is that I would like to introduce what are the fundamental techniques used for measurement of these kind of devices. So these devices are one is called electrochemical measurement and another one is called electrophysiology. So both are based on the electrolyte measurement, and these two methods of measurement is having fundamental difference. Is like in case of electrochemical measurement, we can have the characterizations such as current density or charge density, which is crucial for the having the charge density is crucial for the having the capacity to discharge, charge and discharge capacity, and then photovoltaic impedance spectroscopy. However, electrophysiology is another good technique which evolved since 1950s, and which evolved in such a way that it can give the transient photovoltaic behavior, and we can record even the neuronal functions at placed in the eye. So this is very important. These two techniques are very important, which is widely used in chemistry and physics, and it can be used now here in this kind of applications. Now, before going to my recent works, I would like to introduce with the fundamental concepts involved in this kind of work, which is good for the broader audience who are listening, and some people must be having the motivation for research in the field of bioelectronics. So let's have the fundamental concept in the sense that what are the neurons doing there at the cell, and what are the cell, what is the cell, and how we are going to place our device, and what how it works. So if you see that we know that living cells which are having the plasma membrane, and this membrane is having the head and tail group. So head groups are water loving groups and the tail groups are water hating groups. So basically these head groups are and tail groups are aligned like this. It forms a membrane, so a barrier for the different type of electrolytes. So inside the cell, that is called intracellular medium, and which is dominant by the potassium ions, and outside the cell, which is having extracellular medium, which is dominant by the sodium ions. If you see here, 130 to 160 millimolar. So these two ions are working as electrode. So basically ion electrode. So the two ion electrodes are separated by this plasma membrane. It works like that there is a insulator between the two electrodes, and it behaves like a capacitor. So this is the basic idea about the membrane. And then what happens about the membranes, how these charges, the sodium ions and potassium ions, are responsible for changing the concentration of the ions in the different media, like extracellular media and the intercellular media. So if you see that there are some specialized proteins, these specialized proteins are voltage gated. So basically, if you change the ion concentration, so because of some external stimuli or internal stimuli, if these gated channels are open and the sodium starts flowing the other side and the potassium starts flowing the different side, it starts changing its concentration in the extracellular and intracellular medium. And in this way, it is going to change the potential across this plasma membrane. So what happens in the resting position, these potentials, this cell is having the potential with respect to the extracellular medium around minus 70 to minus 80 millivolt. And this minus 70 to minus 80 millivolt is the resting potential. And whenever some external stimuli comes into picture, this minus 70 millivolt is going to change to some other voltage and going to give you the response corresponding to that. So to understand this one more, as I talked already, that these are having the gating mechanism and there are different proteins are responsible for that. But some of the parameters which are important for this experiment, these are the potential, current, resistance, conductance, capacitance, and charge. These are the very fundamental electrical parameters which are required for this kind of measurements. So if you go to further to understand what is happening at the neuronal action potential, so if you see that, I'm going to describe the two type of action potential, which is related to neurons, and one is related to the cardiac muscle action potential. So both are having similar kind of behavior, and this kind of application can this kind of devices can be used for both kind of stimulations. So if you see that neuronal action potential, as I talked, that resting membrane potential is minus 70 millivolt. And this minus 70 millivolt, when an external stimuli comes here, what happens, these photoreceptors are, which we are replacing artificial photoreceptor semiconductor devices. So what happens that it starts, it opens the specialized proteins in such a way that the the sodium ions going from extracellular medium to the intracellular medium. So the positive potential increases, and it increases to minus 55 millivolt, which is threshold of this one. After this, what happens, this these voltage gated channels have self response, and they start depolarizing after threshold, and they depolarize until plus 40 millivolt when sodium ions in. And then when potassium ions out, it starts repolarizing after reaching to the action potential, and it repolarizes, then it goes to the hyperpolarization and comes to the resting state. So basically this whole phenomena is considered as a one action potential. And this one action potential, with this one action potential, what they do, like they, with this one action potential, the information goes through the axons to the brain. And so the multiple action potential, and it is going to the brain, the cortex part of the brain, where the image processing happens, and we can perceive anything from eye. Next is that, which is cardiac muscle action potential. So you can see that the similar kind of behavior where membrane potential is changing from its resting potential to the depolarizing, and then there is a phase 2 where the calcium and potassium are moving towards that, and then rapid repolarization and go to the resting potential. So with this, we can understand that this is an important parameter which tells us about the device capability and device applicability and feasibility in this direction. Let's go to some theoretical principle which is required for understanding this behavior, which are very basics. And if you see that, as I talked, that there are two conductive ions. One is the intercellular medium and another is the extracellular medium. And there is a in between plasma membrane. So it forms the capacitor. And at equilibrium, there is a resting potential. So at this resting potential, what happens? The force by which the electric field is pulling potassium ions inward is exactly the same as the diffusion force pushing the potassium ions outward. As you know that the potassium ions are in high concentration inside the cell, so they start diffusing. So there is a diffusion force, and it starts going towards the extracellular medium, and then there is a balance happen, and that balance, at that balance, this is the resting potential generated. What happens corresponding to the that the charge movement per unit time is the dq by dt, which is represented as the current, and then further we can correlate this with the membrane potential and the potassium ion movements. So the important point here is that here the charge conduction happens through the ions, not the electrons, not the protons, or not the any other charge carriers, but it is the ions. So we need to understand that uh, this physics is related to the ion movement rather than the electron movement in the biological systems. Next, to understand much more clearly that what is the charge storage happening at the plasma membrane because of the presence of sodium ions and the chlorine ions inside this intracellular medium, we can make an equivalent diagram, and which is having the one capacitor and the leakage resistance there, and there is a membrane potential. So with this diagram, we can understand that what is charge carrier around across this, and which is given by membrane potential multiplied by capacitance. So another parameter which is important from our physics knowledge, that the physical dimensions of membrane is important as well. So from this relation, where A epsilon R D, where A is the area of the membrane and D is the thickness of the membrane, which is from here to here, and epsilon R, which is electric permittivity, and we know that the electric permittivity of these kind of biological systems are in between the 3 to 6. So with this relation, we understand that the area part of the membrane, which is also important in this kind of work. Now, I hope I made some point here about the theoretical and experimental basic points, which is important for this kind of experimental work and this kind of application. Now, from here onwards, I'm going to talk about the two different criteria. As I talked, that the cones are related. There are two types of photoreceptors, rods and cones. So rods are related to the low light intensity vision, and the cones are related to the color vision. So what we are going to see first, that these are the two important aspects for the research in this field. So first, I'm going to tell you the photoresponse at low light intensity. So we had tried to achieve some device which is having the low light intensity response, which is enough for evoking the action potential. So let's see. So what we had the approach here, that we made an organic and inorganic hybrid. Why? Because we know that the organic compounds, organic polymer semiconductors, they don't have the similar performance as inorganic semiconductors. So inorganic semiconductors have high electrical mobility, high electron carrier mobility, and large diffusion length. However, organic semiconductors have diffusion length within the range of 20 nanometers. So that's why they need the bulk heterojunction kind of acceptor and donor mixing. So what we try to use the fundamentals of the hybrid devices, in which we mix the organic and we made the bulk heterojunction of organic and inorganic, both type of semiconductors. And what we saw that if you see, we used here P3ST PCBM as an organic polymer, and P3ST is the organic donor polymer, and PCBM is the organic acceptor polymer, acceptor small molecule. And mixing of these two, the absorption level, you can see from here that the P3ST is having good absorption in the range of 400 to 700. That is the visible region of for eye perceiving any thing from the eye. However, if you use the PVS quantum dots, which are like successfully demonstrated by the solar community, that the PVS quantum dot is having the very much potential in improving the efficiency of the solar cells. So with the PBS quantum dot, people are now getting the more than 10% efficient devices. So by mixing these two, we can see that there is a band alignment. If you mix with PBS quantum dot with appropriate quantity, there will be the band alignment which is supporting the electron transport towards the one side and the hole transport to the other side. So these kind of specific properties we utilized for our device. And what happens, okay, so this bulk heterojunction we made it. So I thought, like, let me put one slide about the solar cell working and how it is going to work into the with the biointerfaces. So for the biological devices. So what we did, what I will show that here the solar cell working, and then I will try to show you that how we are going to switch to the bioelectrical devices or biointerfaces. So if you see here, what happens in the operation mechanism of solar cell, that this is the donor material and this is the acceptor material. So if light shines, there will be exciton generation, and this exciton generation, after that exciton diffusion takes place, which is the range of which is in the range of 20 nanometer, and then it reaches to the acceptor by difference of this electric potential at the interface, and it forms the polarons, polaron electron and polaron hole, and after that there will be free charge carrier formation, and then it moves towards the respective electrode. One is here and another one is here. So what is the trick here to use this device into the biological devices or for neural retinal prosthesis? What we did, that we replace this aluminum electrode, the one side of the electrode, with the biological electrolyte media, and where the neurons are placed. So we put this whole device, which is having the transparent electrode, at the place of the photoreceptor. So this was the idea. So the electron will reach anyway at the biological electrolyte media, and the holes will reach at the ITO. So this way we separate these electron and holes, and here we expect some kind of capacitor kind of behavior. So with this, with this idea, let's see what is happening with the, so before going to the biological devices, what we did, that just a representation that we use glass, ITO, zinc oxide and photoactive layer, and this zinc oxide photoactive layer, here we use zinc oxide as an intermediate layer between the photoactive layer and ITO, and we remove this molybdenum oxide and silver, this portion. So we use this for now to show you that the impact of lead sulfide quantum dots in the bulk heterojunction of the P3ST beam. So what happened, we saw that there is an enhancement of more than 20 times, like 5-fold increase in the current density, which is required because we want more and more charge accumulation at the interface of biological media, so that we can have the more external stimuli even at a low light intensity. So this was very promising point. And then what we did, like for further understanding the why it is increased so much current because of the lead sulfide quantum dots. So we saw that there is not much difference in the visible spectrum. So the absorption, so since the absorption doesn't have significant increase, so what could be the reason behind having this such a high current? So we went to AFM and checked the morphology and found that there is a smaller intermixed phase separated domains created because of lead sulfide quantum dots. So because of this smaller domains, we found a good transport of electrons. So you can say that band alignment was good, absorption not much, but there is enhancement, and there is enhanced morphology. So morphology was the critical point which gave us the higher electrons at the interfaces. So having this idea about this device with respect to the photovoltaic devices, we started working on biointerfaces. you can call biointerface or photoelectrode. So in this we designed three type of devices, because there is a one important parameter which I discussed in the previous slide in the beginning, that the capacitive mechanism of charge transfer is required rather than the Faraday charge transfer. So we designed the device one without ITO. There was there is a protective layer and with ITO, and then glass substrate, and there is an intermediate layer. So what we did, like we didn't put any intermediate layer. It was with ITO and protective layer. So this is the band alignment corresponding to that. Then we put the molybdenum oxide in between the ITO and photoelectrode layer, and to see that the band alignment gives us that whole movement towards the ITO and electron movements towards the biological interface. However, when we put zinc oxide, the band alignment tells us that towards the ITO, the electron will come here, and we are going to put the biological interface at this place, so the holes will be there. So what will happen? Sorry. Oh. Yeah. So what happens that when we use this one, when we use this three different type of designs, then we try to measure the photocurrent corresponding to this one. And photocurrent we measured with the help of our electrophysiology system. So in this electrophysiology system, if you see that we put the ACSF solution, which is extracellular medium, and there is a patch pipette that is having one electrode AgGCl, which is close to the protective surface, and then there is a amplifiers and to gain the external output, and then there is a ITO which is connected to the second negative part of the, so it is basically grounded. And these are the protective layer, intermediate layer. So what happens when with the type 1, we saw the very high Faraday current, like 12 nanoampere, which is not good for our devices. Then we went to the molybdenum oxide kind of device, which is type 2, and we saw that this Faraday current is controlled a bit. In fact, hugely controlled. It's a 0.7 nanoampere only. But when we put the zinc oxide, it shows the capacity behavior of the charge transfer. So if you see that this is the charging, it is showing charging, and it is reversed, because when we put zinc oxide, the holes start moving towards the protective layer, and towards the ITO, it is the electrons. Because of that reason, it is reversed. So this is the charging, this is the discharging. There is a slow discharging, which is related to the material property. And then, so we found the capacity mechanism, and when we calculated the area of these two parts, the on and off time, so we found that it is almost equal. So which shows that it is a pure capacitive behavior of the device. So with this behavior, what we did that, and I forgot to tell you that when we shine the light, we see this kind of behavior, and this light is a pulse light, which is on and off. It is the blue light, 450 nanometer, 10 millisecond, and 1 milliwatt per centimeter square. So this is the intensity is 1 milliwatt per centimeter square. It is very low intensity if you compare the solar cell operation at 100 milliwatt per centimeter square. So 100 times lesser intensity than the solar intensity. So one can imagine that it will be very critical for the vision in the low light, in the evening time or even in the night. So this is very important finding with this device. And what happened that we measured we characterized it further for the second aspect, which was we need wireless and freestanding device. So what we did that, which is real device operating condition, because we are going to put the device inside the eye, and we are not going to connect the ITO with anything else, any wire outside. It will be the freestanding. So if you see this device is freestanding in the ACF solution. And what we saw that even if it is freestanding, when light is falling on this, we are getting until 1 nanoampere of current with the help of PVS quantum dots. With the help of without PVS quantum dots, you can see that it is having only 0.3. So almost like 3-4 times of improvement in the device because of the mixture of PPS quantum dots with the polymer semiconductors. So this is showing our criteria, which we assume that it is going to help us. It is helping us very nicely. Like there are 3 to 4 times of improvement. Further, what was the another criteria? That was a third criteria, that it should be biocompatible. So initially we started with the SHSY 5Y. These are the cancer model cells, and these cancer model cells, neuron cells, what we did, it is available in the market and it is made in the lab basically. So very easy to store and easy to process it on the substrate. So we processed it on the photoelectrode, and we processed it on the ITO control as well, and we saw the MTT assay, and this MTT assay has shown us that it is very much comparable to our polymer is having similar behavior in terms of biocompatibility as the ITO. So it is very good in terms of biocompatibility as well. So it satisfies the third criteria as well. Then after satisfying all three criteria, what we did, that we went on to measure the it's a neuronal stimulation part. So what we did, like in the neural stimulation, I have shown that this electrophysiology system. So what we did, that on the photoelectrode, if you see, there is a neuron. This is the real image of SHSY cell, and we are patching this electrode, which is having AGGCL, with the help of patch pipette, and we are inserting it into this one. So it is patching with this one electrode is here, and another one is grounding the this solution. And when light is on, so now whatever we see, it will be behavior of the neurons rather than the photoelectrode. So when the light shines, the photoelectrode will generate electron on hole pair, and holes will start moving towards this neuron, and electron will moving towards the ITO. So what will happen if you see the IV current? So it is having the nice behavior of the this neuron. It is the typical characteristic of the IV for the neurons. And what we did, we went to the voltage clamp mode, where we started measuring the this membrane potential. So this is the neuromodulation potential we can see. Since this SHSY is not the real cell, and it is not the like excitable cell, so that's why we are not seeing the action potential. This is, if you see here, the membrane potential is around 10 to 15 millivolt only. And so from the resting, it is increasing only depolarization, and then it is coming to the hyperpolarization and going back. This is the statistical data for the even load light intensity until 0.1 milliwatt per centimeter square. So this paper we published in Physical Review Applied with this result. But further, what we did, that we replaced these SHSY cells with the real cells in our eye, which is hippocampal neuron cells. So what happens with the hippocampal neuron cells? We remove the hippocampal neurons from the mice, and we put this device inside the eye of mice, and we saw that there is a action potential generation because of this device, even at a very low intensity of 1 milliwatt per centimeter square. Now you can see that these are the real action potentials, and the membrane potential is 20 millivolt. With this, you can see the membrane potential from minus 70 millivolt, it is reaching around minus 20 to minus 30 millivolt. So, and there is a multiple train of the action potential corresponding to the light pulses. So this is a successful demonstration of this device working at a very low intensity. This is the first part of the our work, which was significant with respect to this research. Now, second part, as I told, that there are cones which is responsible for the color vision. So we need to have some switching control, and just because of light. And let's say there is a green light falling on it, there is a red light falling on it, or there is a blue light falling on it. So there is a mixture of three lights and can give the white light. So there will be control over the photomodulation with the help of these different type of lights. And how this is going to control. So it requires a lot of effort. Still, we are in the very beginning stage, but our work was recognized. So let me tell you some of the important parameters which I try to have this kind of control over the neuronal activity. So what I tried, I took the information from the solar cell again, and this in the solar cell we know the one parameter, that is open circuit voltage. So what happens if you understand in the previous part that we are working in wireless mode. So it means that there is no connection. So it is the basically open circuit. So this is the open circuit condition where we work. So in the open circuit condition, so if it is higher the potential, we can correlate it with the higher charge capacity. This was our thought process, and this is the just definition of how open circuit, how it is defined: HOMO of the donor and acceptor, LUMO of acceptor. If you subtract it and divide by charge, you will get this open circuit voltage. And these are the electrical parameters related to the solar cell. So what we did, like using this concept of open circuit voltage, we made two type of devices. One is having the P3HT polymer, and one is having the PTB7TH polymer. This is the another thiophene compound which is having donor acceptor kind of behavior in a single compound. And this material in the solar cell community, this solar cell is having the VOC, open circuit voltage of 0.7 to 0.8 volt, and this P3HT is having the VOC of 0.5 to 0.55 volt. So obviously it is having the increased open circuit voltage. So further we characterize this solar cell. Then we saw the IV performance, and you can see that there is a significant enhancement in the VOC. And these are the devices in the pixelated mode, and there are 8 pixels, and all are responding similar behavior. And then what we did, like we saw the charge transport behavior, and we are going to name the high open circuit voltage device as a BI2 and the low open circuit voltage as a BI1. We put this SEM image as well to see the equal thickness. It is almost having the same thickness, 100 nanometer around. There is a zinc oxide, there is a active layer. Then what we did, like we tried to do the photo current measurement in the electrolyte media. And this is first parameter we always check for the device. So it's the same setup without neurons. And what we did, like once to correlate this function, we just took the UVVs as well. And UVVs, if you see, this is the area where the absorbance is similar for both type of devices. So we need something which is having common absorbance. Then only we can compare with the same light stimulation for these two devices. So we use this 470 nanometer this light, pulse light, for the recording of these two devices. And if you see here, that this red one is having the low open circuit voltage, and the green one is having the higher open circuit voltage. So there is an enhancement of approximately 30 to 40% of current because of only open circuit voltage of the device. And there are other parameters which are important, that with the open circuit voltage, higher open circuit voltage, Faraday current is negligible. So Faraday current reduction is happening with the higher open circuit voltage. And there are rise time and fall time of the capacitive behavior, but that is also significantly improved from 19.9 millisecond to 6.7 millisecond, 2 millisecond. So these eye behaviors, eye phenomena are in the range of sub-micron to millisecond range. So it should not be more than beyond 10 millisecond, because all the eye activity which is happening, this action potential and this kind of things should be in this millisecond time interval. So in that sense also, this high VOC material is giving us significant gain. So further, we use the electrochemical measurement, and then we try to control, we try to see the light intensity control over peak photocurrent. And you can see that it is more or less, you cannot say linear, but it is having a slow decay in the exponential mode. And with this relation, you can understand that this is the JPH and this is the exponential of V minus JRS. So this relation clearly shows that it has this kind of behavior. Then what happens if you can compare the photoelectron, this the VPH photoelectron voltage, that is the with the open circuit voltage. So open circuit voltage is the fundamental of solar cell, and this VPH photocurrent, which we measured with the electrophysiology setup, it is the fundamental of our photoelectrode, and both are having linear relationship in the logarithmic plot, which shows that they follow one to one. So it is also confirming that our VOC, our photocurrent is dependent on the VOC behavior. And you can see that also this rise time of the capacitive behavior is having the exponential decay with the light intensity. So as the light intensity is higher, the rise time is lower. So if light intensity is very high, our eye is very sensitive to that light, and it will blink. So it should be very for very small time. So this is very important factor, which is justified by these two equations, that it is following the similar kind of behavior as it is in solar cell. So what happened, that next process is that after photocurrent measurement and the capacity behavior, we need to have the this cytotoxicity assessment, which is biocompatibility. And we did this time immunobiology and fluorescence microscopy. These are the simple biological steps with which we understand how these neurons on the substrate they behave. So it is the phase images in the different phase image, and with the different staining there are phase images. So with this, we can see that these PTB7TH based materials, which is high open circuit voltage based materials, are also very much biocompatible with for this kind of application. So now I'm going to come to the last part, which is having the neuronal stimulation. That is the last part we need to do to understand the applicability of these kind of devices. And this time, what we did, that we used the real neurons, that is the hippocampal neurons, rather than using the models SHY cells. And these are the real neurons, and it is having nice axons which can communicate the signal from here to the other cells. And then it's the same setup. And then what we let me show you the phase contrast image of these neurons. These are the different neurons, and it is connected with the axons. So the signal at let's say axon potential generated here, that can travel through this one until here or here. Once this is the way the information goes from one neuron to the other neuron. Then what happens, we did the IV characteristic, and for number of cells, like to have the statistical data, and we can see that here minus 70 millivolt is the statistical data showing that the resting potential is around minus 70 millivolt, which was the case for the real neurons. So now we are very close to the real situation of the biointerfaces. Now, if you go to the next level of measurement, that since these neurons are very sensitive to the different things. So what happens, sometimes these neurons are having two type of, you can say, spontaneous activity. So even if you put the light, or even if you put something, some external stimuli, before that they can have the action potential. So it will be misleading, and it will not have the clear information about whether it is from the photoelectrode or it is because of its internal spontaneous behaviors. So to confirm that one, what we did, that we used neuronal hippocampal cells on Petri dish. So there is no photoelectrode, and we start shining the light, and we can see that it is around minus 70 millivolt. It is having just a normal fluctuations. There is no photostimulation and no action potential. So this makes clears us that there is no spontaneous activity in the neurons without photoelectrode. So what we see that in the next picture, that we did this on the 10 neurons at a different substrate, and we found that when light was off, that there is no stimulation, not at all. It is just similar to the Petri dish behavior. Now it is on photoelectrode. So when the light is on, you can see that there is a threshold potential rise. There is a rise in potential which is reaching to the threshold value and then going to the action potential. And nicely it is coming back to the hyperpolarization and then resting potential. And it is having similar behavior for 10 type of 10 different neurons with on a 10 different substrates. So this is very critical in, result for this kind of using this kind of devices. We are getting the actual potentials, actual stimulations in the neuron cells. So with this, I would like to summarize my work, and I've shown the two different directions of the works, which this is not only the two different directions, there are many directions of the works, because there are neural coding is required for getting the real color vision distinction and all these kind of things. I summarize this work in the sense that that it will be like general summary rather than the specific summary to the our work. So what is there, that there is a need of multidisciplinary work for this kind of research work, which is very much required for our health system. And it involves the chemistry, it involves the physics, it involves the biology, and all and electronics and all such kind of. So this is multidisciplinary activity. This bioelectronics has immense scope in the students for any discipline, as I said. And this is the one application which I discussed, that is eye. But in our body, a lot of neurons are there in different places, and a lot of different neuronal activity happening at a different, at a heart, at a spine, at a in a stomach. And there is a diseases like blindness, Alzheimer, cardiac muscle stimulation. These kind of diseases can be cured in future. And these diseases are very much prominent in our society because of our lifestyle. So it is important area to have the research so that we can directly contribute to the society, to the welfare of the society. Now, these photovoltaic devices, which was one of the key solution for energy sector, it can become a key solution for the neuronal processes as well. There are a lot of work is required in terms of our characterization techniques as well, because there are very small you can say side effects or artifacts are there in the electrophysiology technique. So people are working on the device the characterization technique side as well. So this is one of the area where many people from mechanical background, from electrical background, they can work on this as well. And the self-reliant, sustainable, and biocompatible devices are required for the future healthcare solution. This is the last closing statement I can say. And with this, I would like to close the. I would like to thank my colleagues from the Koch University, Mr. One PhD student from Rustam John Meliko, Meredith Boss, and there are two different supervisors, one from biological section, Ibrahim Halil Kawakli, and Professor Siddharth Nijamoglu, under whom I'm working on this European Research Council project. And we are getting the funding from Koch University and the ERC, which is the consortium of different industries in the Europe. With this, I would like to thank, I would like to end this presentation. Thank you very much.
Thank you very much, sir. Really, it's a great talk. There are so many questions from the audience. So can I ask you now?
Sure. I'm ready.
Yeah. So the first question, photostimulant, does it affect the opsin and rhodopsin cycle of vision?
Sorry, oxidation and reduction cycle of vision.
Yes. No. Opsin and rhodopsin cycle of vision. Photostimulant.
Photostimulant. I didn't get your question clearly. Can you repeat it again?
Photostimulant, does it affect the opsin and rhodopsin cycle of vision?
Okay. Now I got it. So see, these photostimulants will be replaced in place of photoreceptors, and these are very much biocompatible with the closing environment. And we checked it with the 1 month of putting this device inside the mice eyes, and we saw that there is no deteriorating effect on the rhodopsin and opsin.
Okay, sir. Sir, another question. Type 1 and type 2 devices showed positive photocurrent response, while
Yes.
type 3 showed negative response. Why?
Huh. So I think I explained, but let me go through it again, because in type 1 and type 2, if you see the band diagram, the movement of yeah, here if you see the band diagram, so type 1 and type 2 are having in which the movement of electron is towards the PCBM. So, and because of the presence of this MOX and ITO. So, and if you see the band alignment, when I put the zinc oxide in type 3, zinc oxide is electron acceptor. So I'm putting it towards the ITO. So it is not going towards the P3ST and PCBM, rather it is going towards the ITO. So the charge carrier at the interface is changed from electron to hole. So the response from the electric current will be reversed.
Okay, sir. Uh, Sir, another question. You
Mm-hmm.
claimed SHSY cell is biocompatible. Did
Mm-hmm.
you check LD50 values for your quantum dots?
Not really, not really. We are working on this one. The quantum dot things are now like, let me tell you right now in our lab with the limited resources, we have started seeing the behavior of quantum dot specifically for the biocompatibility. So it is the combination of the things, and here the quantum dots in this device is used in a very less quantity. It is like 3 to 4% of the whole volume of whole weight of P3ST PCBM. So that's how it is not going to
Sir,
affect much.
okay, sir. Uh-huh. Sir, last question.
Yes, please.
Why don't you choose photocapacitance as your output response parameter as
Mhm.
you took capacitive based materials?
Again, sorry.
Why don't you choose photocapacitance as your
Mhm.
output response or parameter as you
Mhm.
took capacitive based materials?
Okay. So you are asking like why I'm
Yes, yes,
choosing capacity mechanism,
yes,
right?
sir, yes, sir, yeah.
Yeah. So the important part of thing is that when we place our device at the interface of neurons, what happens? The around the device there is a electrolyte media, like it is the water media with the different ions, potassium ions, chlorine ions, these kind of ions present at the surface. So what happens when the electron reaches to the surface? They will oxidize, they will reduce these potassium ions and calcium ions. So if any kind of reduction happens at that place, it will be the permanent, and there can be permanent damage to the different means it will reduce the concentration of the ions in the solution. It can also deteriorate the different part of the biological interface as well, with the reduction and oxidation behavior. So what we try to do that, we try to control by making a virtual bilayer at the interface, which is having only the charge storage rather than rather than indulging into the oxidation and reduction reaction. So that's why it is very important to have the capacitive mechanism in which the charges which is going to the interface is going to come back when light is off. When light is on, it will go to the interface, and when light is off, it is going to come back and recombine. So it will be beneficial for the device lifetime in the eye, because if by after surgery, if you are going to put this device in the human eye, it should be having life around, let's say, for old age people, at least 10 years. For genetic people, for the young people who is having this disorder because of genetic modification, genetic disease, they need like 25 to 30 years at least. Otherwise they need to change a device frequently after surgery. So that's how it I hope it explains why photocapacity mechanism is important.
Okay, sir. So really, it's a nice talk and enormous knowledge we have gained from the audience point of view.
Yeah,
So
thank
from
you
the
very much.
organizer, I would like to thank you once again, sir. Thank you very much for your presentation.
Yeah, thank you very much.
Now I would like to call Professor Vanakar, sir. Please share your screen, sir.
Yes, thank you. Hello.
Sir, you are audible.
Already.
Sir, your voice is not clear. Can you speak loudly little? Not yet, sir. Not clear actually.
Okay, is it okay?
Yes, sir. Now it is okay.
Okay, thank you. This is maybe the problem of mic.
Yes.
Okay, thank you for inviting me. First of all, very nice presentation by Dr. Srivastava. Very good presentation, and he already given one advanced materials for solar cell, and even though for biological or biocompatible devices or in biological field. This is one of the hottest area of research right now. Thank you, Dr. Srivastav. Uh, Thank you, Dr. Rajnikant Nimbalkar and all other organizers for inviting me to deliver a lecture on advanced material. Myself is Dr. S.A. Vanalkar. I am working as an assistant professor at KH College Garguti. And today I am going to discuss on general description of or general discussion of advanced material. Uh, Dr. Srivastav gives a clear idea about one of the recent trends or recent advances in material science. Actually, I am going to discuss some general about material research. This is outline of my presentation. Basically, advanced materials are related with one of the field or one of the stream of science and technology, which is nothing but a material science. So first of all, I will discuss what is material science. Then we will discuss advanced materials, which are the recent advanced materials we will just go through. And if time permit, we will check out the recent advances or materials in solar cell or solar cell technology. So material science, we know that material science is a interdisciplinary field of science and technology, which deals with the study of designing and discovery of new materials, which can be applied to various areas of science and technology. It is a very broad field. It involves application from a number of scientific disciplines and contributes to the creation of new materials, we can say. This field is made up of peoples with the different backgrounds, like engineers, scientists, physicists, chemists, nanotechnologists, material scientists, and so many. In material science, we always focused on the properties of material like strength, hardness, flexibility, electric and magnetic or thermal conductivity, then catalysis, stability, uh, yes, low cost and ease of synthesis. So these are the some of the characteristics or some of the properties we have to take care as far as the material scientist is concerned of that materials. Based on these materials, we can apply them in our daily today materials. As far as the history of solar cell, history of material science is concerned, okay, as far as the history of material and material science is concerned, it is starting from our origin, because our origin because our history has been defined by the materials we use, like stone, copper, bronze, semiconductors, and all these are the materials. So that's why I already says that the history of material science starts from our origin. Man has been studying material science since before leaving the cave, well, we can say, because the first tool was developed around 6,000 years ago. We can use different materials. As far as the material science is concerned, the materials can be classified into four main groups like metals, polymers, ceramics, and composites. Metals are the materials that are normally combination of metallic elements. Metals, we know that they have good conductors. Metals usually are good conductors of heat and electricity, and also they are quite strong and lustrous look when they are polished up. There is another kind of material which can be used in material science is polymers. Polymers are generally organic compounds based upon carbon and hydrogen, and they are very large molecular structure. Usually they have low density, and they are not stable as far as the harsh environment is concerned. But to sustain in harsh environment, we will go for another type of material, which is nothing but ceramics. Ceramics are generally a compound between metallics and non-metallics elements, and typically they are insulating, resistance to high temperature, and we can which can withstand in a harsh environment. There is another one kind of material which is very popular in material scientists or in the as far as the material science is concerned, this is a very hot materials we can say, which is nothing but a composite. And composite which consists more than one material type. For example, if you consider fiberglass, then it is a combination of glass and polymers. There are the number of composites, and we will discuss, if time permit, we will discuss some composites here. Okay, we'll just go through all these four types of materials, and then we will discuss about the advanced materials. Actually, metals, we know that these are the some elements which are good conductors. In periodic table, we can see metals and non-metals separately. There is another one. There is another one category which is we can say alloy. Alloy is a homogeneous mixture of two or more elements, and the metals and alloy gives some properties like high tensile strength. They have magnetic and electrical properties also. They have high electrical conductivity, and that's why they are used in number of applications. There is another one class which I already discussed, that is a composite. Actually, composite is a two inherently different materials when combined to produce a material with properties which exceed the constituent materials. For example, if there are two materials, one material has electrical conductivity suppose X, and the second material have electrical conductivity suppose Y. If we combine them, then electrical conductivity is more than X and Y. So this is the beauty of composites. So composites give you enhanced property, and that's why composites is also nothing but called as an advanced materials. We will discuss why it is called as an advanced material, what is nothing but the advanced material. Before that, there are two types of composites. One is reinforcement type of material, and second is matrix. Reinforcement type of materials consist carbon or fiberglass. They have high tensile strength, stiffness, impact resistance. So these are the good quality of this material. While the matrix materials, which have chemical and heat resistance, both materials offers high strength, lightweight, and design flexibility. That's why they are used in number of applications like helmet and bulletproof jackets are made by these composite materials. Even those aerospace or all other things we can manufacture by using the composite because of low cost and easy in processes and lightweight, flexibility, stiffness, tensile strength. All this property will give you a good kind of material, or we can manufacture a good kind of material by using the composites. There is another one type which I already discussed, like ceramic. Ceramic is another kind of material which is commonly used in material science. Ceramic is an inorganic non-metallic solid prepared by the action of heat and subsequent cooling. Number of ceramics are available like clay or oxides like zinc oxide and all other materials. We know that the ceramics gives us a strong solid inert property. That's why they are used in number of applications. They withstand chemical erosion due to acids and caustic also, and I already told that they withstand in harsh environment. They can withstand in temperature about 1000 or more than 1000 degrees Celsius. On the other hand, polymer, which is high molecular weight, which is made up of small repeated unit, which is we called as a monomers, and there are a number of materials. We know that these These can be used in some applications. I'm not going into detail of that, but there are two types of polymers. One is called as thermoplastics. This can be processed by melting several cycles of heatings and cooling. And next one is the thermosets, which is nothing but a good quality of polymers. Apart from that four materials, there are other sorry. Apart from these four, there are other materials. The slides are not running well. Sorry for that. Okay. More important classes of materials apart from the metals, polymers, ceramic, and composites are catalysis, then semiconductors, superconductors, ionic crystals, inorganic classes, and so many number of materials we can use in material science. Now we'll discuss about what is advanced materials. Okay, so the name itself suggests that the material that utilize high technology applications, which terms as an advanced materials. For today's lecture, we will actually bifurcate materials into two categories. One is the regular materials, that mean which is we can say conventional materials, and second which is we called as an advanced materials. Advanced materials means the materials which can be engineered properties by various means, by developing specialized processes, synthesis technology, or which includes lot of ceramics to biomaterials. And these are actually traditional conventional materials, but whose property has been enhanced. Something new is developed or something high performance is developed, then this material is termed as an advanced material. They may be any kind of metals which we already discussed. It's maybe metals or composites or maybe superconductors or maybe ionic liquids or maybe anything, but its property should have to be enhanced or its performance should be a superior as compared to the traditional or conventional materials. And the advanced material includes semiconductors, biomaterials, smart materials, nano engineered materials, and so many. And the properties of these materials are, as already told you, they have superior properties as compared to their traditional counterparts. Now, how we distinguish the conventional materials and advanced materials? For that, we have to start one survey. Okay, we have to ask one or two questions to that materials or the scientists working in that field. The question like, is the material specifically specially engineered or having a novel or enhanced properties? If the answer of this question is no, then obviously the material is not advanced. This may be a conventional material. Conventional materials means a material which does not have enhanced property or superior performance or any kind of novelty. If the answer of first question is yes, then we have to ask another question like, do the novel or enhanced properties confer superior performance relative to the conventional materials? Okay, the first question is okay, yes, but at the same time your material should have to show some superior performance. If the material have some novelty, if material have some enhanced property, even though it does not shows the superior performance, then once again this material is called as a conventional material. If the answer of both this question is yes, then and then only we will say this material as an advanced material, because the advanced material having novelty as well as enhanced property in addition of superior performance. So we have to consider three properties when we are saying advanced material. Then advanced material should have novelty, the advanced material should have enhanced property, and it should have superior performance. Okay, so the classification of this material, we can classify the material as enhanced or novel. Before to proceed further, you should know these two terms, novelty and enhancement. Novelty or novel is a new or not resembling something formerly known or used, which is maybe a physical property or chemical property, or it's maybe a entirely new physical phenomena or chemical phenomena. That is nothing but a novelty or novel material, we can say. Enhanced, that means which is increased or intensified or improved quality or value or extent or what it may be. It should be enhanced as compared to its preceding counterparts. Superior, it should be better than average and better than others at same time. Then this material is called as an advanced material. Actually, advanced material uh, advanced material is a result of so many or components or combination of so many components, like it is a combination of physico-chemical or biological attributes inherent to the materials, or it's maybe a novel use of applications of conventional materials. If you say the material has physico-chemical or biological attributes, greater or superior biological or physico-chemical attributes, then it is called as a first type of advanced material, which is we categorize again 1A and 1B. 1A have an enhanced property as well as inherent physico-chemical biological attributes. Second is novel property and these physico-chemical biological attributes, which is a good one. Second one is the novel use of applications or of these conventional materials. So you can use conventional materials, but you have to apply this in a new area. Then it is also called as an advanced material. I'm not going into detail of its subcategories. There is another one. It is a unique combination of conventional materials, and maybe the advanced material is also called as the material have developed the additive manufacturings. So your material is said to be advanced material if it falls into these categories or fall into one of these categories. Okay, so these are the very good parameters which decide the advanced material or criteria of advanced materials, we can say. If time permit, we will study all these attributes here. Sorry, all these parameters here. Now we'll go through some of advanced materials. Actually, I'm listed here some advanced materials from last 50 years. This is just for our discussions. Maybe it does not include some advanced, actually real advanced materials. Because of time constraint, I put here just 5 or 6 or 7 materials, which is considered as an advanced right now. The first one is the giant magnetoresistor. Because of that, number of scientists got a Nobel Prize in 2007. Giant magnetoresistor is a quantum magnetoresistance effect, which is observed in thin film particularly. Actually, I'm working in that area, thin film, not in magnetoresistance, but in that area. So that's why I put this effect as the first advanced material in my list. Actually, it is the way to control the resistance at nanoscale, particularly by using the magnetic effect. So this is a good material. There are a number of materials are used for the giant magnetoresistance. Another one is the materials which are used for semiconductor lasers and LEDs. Actually, we are going for a go green type of survey. Okay, peoples are trying to reduce the energy consumptions, and for that they are using number of devices. So actually, light emitting diodes is one of the devices which less consume your energy, which save the energy as well as save our environment. The development of semiconductor lasers and light emitting diodes was started in 1962. This is a great material science story, and they are now the basis of telecommunications, CDs, DVD players, laser printers, barcode recorders, and so many. This is one of the advanced material. Number of materials are right now using for the construction of semiconductor lasers and LEDs. So this is one of the hot area as well as the hot advanced materials. Our list will not complete by naming this CFRP, carbon fiber reinforced plastics. These are the lightweight, strong material used in manufacturing of number of products used in our daily life. A lot of expensive cars are built by using this material because of this steepness and high end strength. This kind of material, this kind of composite CFRP is a continuous carbon fiber organic matrix composite, and this matrix is very steep, high strength. That's why they are used in very harsh environment, even though they have very lightweight also. So this is a we can say an advanced material in material science. The list will not complete without mentioning the materials used for lithium-ion batteries. Okay, it is hard to think about the age before laptops and mobiles. Even though this kind of online presentation or online seminars will be not possible without laptops and mobiles. And these kind of devices are right now popularized and everyone are using because of these lithium ion batteries. The conventional types of batteries was not that much effective for mobiles or what we can say laptops. So thanks the lithium ion batteries and the material used for lithium ion batteries. Lithium ion batteries require the development of novel electrode material that satisfy the number of applications and considerations. Actually, they are lightweight, and these are we can say one of the hottest material, hottest topic in material science. And day by day, there are lot of researchers are invented lot of materials for lithium ion batteries, and there is a lot of scope. You can work or you can discover a lot of materials which can be used in lithium ion batteries. Okay, so this is one of the advanced material which in current scenario. Obviously, the next one is the carbon nanotubes. Actually, the carbon nanotubes was discovered in by Izima in 1991 in Japan. In last 20 years, it becomes one of the hottest material in a research area in material science. The observations of nanotubes of carbon had actually been made on previous occasion in 1991 also. However, the excitement of discovery of carbon-60 or buckyballs in 1985, a form of carbon, Ijima observations and new fluorine type carbon nanotubes, which are recently used in many of area. Today, the remarkable and unique phenomenal promising properties of these nanotubes are have placed them right among the hottest topics of material science. Actually, they are not at the top because there are a lot of issues related with the carbon nanotubes, like synthesis, purification, large scale production, assembling into devices. So these are some issues related with the carbon nanotubes. But in near future, the researchers will overcome all these difficulties, and it becomes one of the great advanced materials in science and technology. As far as the market, carbon nanotube market is concerned, by seeing this figure, you can understand how the carbon nanotubes are essential or becomes in advanced material, because the electrical and electronic market share, that the carbon nanotubes are taking 10.6% of electrical and electronic market share right now. And it is predicted that the carbon nanotubes market share will increase from 4.56 billion right now to about 13.65 billions in next 5 years. So you can understand how important this kind of material is. I'm not going into detail of all this, like what is the current market in America, but right now everywhere you can see the importance of carbon nanotubes. Another advanced material, it's nothing but a meta materials. It is the beginning of new millennium, brought a great excitement when it was conclusively demonstrated that a material with a negative refractive index could exist. So this is a good kind of invention. Light or at least microwaves would bend the wrong way on entering this material according to the standard Snell's law of refraction. And this material have negative permittivity as well as negative refractive index. You can imagine what is meant by negative refractive index. The material which negative refractive index, what will it gives, like a Mr. India or anything like this. So it is one of the advanced material we can say right now. Okay, it is actually metamaterials. First metamaterial was a composite of metal wires, which is split rings assembled on a lattice or printed circuit boards. It was an example of metamaterials, and it is an artificial structure of repeated micro-sized elements designed for specific properties. Great work can be done in this area also. Okay, the next one is the materials used for solar cell construction. Right now, there are a number of materials are used to construct the solar cell. The this marathon was started from silicon, and then till today there are a lot of materials are using, like organic, inorganic type of material, like perovskite type of solar cells are using, perovskite type of materials are using. So these are the number of materials we are using to construct the solar cell, like silicon, Then people's used CIGS, CZTS type of materials. As far as the advanced materials are concerned, in solar cells, perovskites is one of the good advanced material we can say, which is used to construct solar cells. So because of time constraint, I'm not going into detail of all these best cell efficiency cell, which published by NREL. But you can see the red colors. These devices are nothing but advanced materials, and which also giving a good kind of efficiency. Now, the next one, we can say the materials used for artificial sensors. This is, we can say, advanced materials. Actually, I'm giving some of the examples of advanced materials, but the list will continue. There are number of another materials also. But this is, we can say, last material I'm noting here. I'm giving here the materials for artificial sensor. Actually, artificial sensor which is also called as e-nose. It is plays a critical function in robotics by mimicking the human olfactory organs that can recognize different smells that correlates with the range of fields, including environment monitoring, disease diagnosis, public security affairs, or agriculture production, or even the food industries. In current coronavirus pandemic situations, we can realize on these artificial sensors also, because these disease can diagnosis with the help of e-nose. So I think in next few years, this will be a hottest area of research, and the materials used for artificial sensors will be huge importance in coming years. The artificial the e-nose will work as similar as the human olfactions, that mean human nose work. The odor receptor, then brain, then neuron systems, and we will get the flavor of what we are. They are like green tea or anything else. In artificial these artificial sensors also, there are some materials which can act as an odor receptors, and then they can send us signals in various form of electrical forms to sensing signals, and they can be analyzed by some system ANN, and they can recognize, as in case of in our case it does by brain. So this kind of artificial sensors work similar to our human olfactions or human artificial sensor. In current pandemic situations, this can be used. The breathing analysis can be done using this artificial sensors. So there is a lot of scopes. Actually, because of time constraint, I'm not going into detail of all these things, but this is one of the hottest area of research, one we can say. So by using just breathing, we can analyze any kind of disease, or we can diagnosis. Even though peoples are using for diabetic diagnosis, peoples are using this kind of artificial nose or artificial sensors. But there are scope. We can in near future we can see corona like viruses by using this kind of advanced materials. Okay. Now, as far as today's lecture is concerned, I'm talking about the solar cells and advanced materials in solar cells. So we'll discuss this part in very brief or very limited time. Actually, solar cells or photovoltaic devices are the devices which convert light into electricity. Solar cell is a very small device, actually having 1 or 2 centimeters or having less area. But to make a photovoltaic system, we have to go the number of steps, like we have to assemble solar cell by series or in parallel combinations to make a solar module. And these solar modules can be combined to form a solar panels. And all the solar panels, when combined together to make a photovoltaic system, as in a few days back, Prime Minister Modi ji already inaugurated the photovoltaic systems in Madhya Pradesh. So we know that. So this photovoltaic system can be used in number of field, like electricity generation, electric meter, battery, charge controller, generation of meters, DC isolators, cabling, mounting, tracking system, even though in satellites also. So there are a number of applications of photovoltaic systems concerned. Now, as far as the advanced materials is concerned, what is the advanced materials in solar cell? Basically, solar cell was invented long back. People are using solar cells to produce electricity. Then what is advanced technology, advanced materials in solar cell? So we will discuss in our coming slides here. So we'll start from some solar cell background. In 1839, French physicist Becquerel was first recognized the photoelectric effect, followed by the first solar cell was built using selenium semiconductor, which is coated over a gold to form a junction. This was the first solar cell. After that, 1954, in 1954, Bell Laboratory was like, that was an accident. They experiment with the semiconductors, and they found the very useful solar cell which convert light into electricity, and that the solar cell efficiency was around 6%. So we can say this is modern solar cell was invented in 1954, followed by next few years in 1958. This kind of solar cell was used in spacecraft, and right now we know that everywhere, or in particularly satellites, cells are used to generate electricity. We'll go briefly how the solar cell work. This is for the persons who are not from solar cell background, or persons from not material science background. For those people, I'm going to show how the solar cell work. Actually, solar cell is a combination of p-type semiconductor and n-type semiconductors. It generates electricity by using sunlight to make electrons to cross through the junctions. When the sunlight is incident on the semiconductor, for example, if there is n-type semiconductor is at the top, then the n-type semiconductor having electrons as a majority charge carriers, they absorb the sunlight, photons or light particles we can say. And by using this energy, because photons or light have some energy, and the electrons from n-type semiconductor absorb this energy, and with that energy they cross p-n junction and goes to p-type semiconductors. And yes, then the when they cross the p-n junction, electrons use this energy to jump the barrier, and then they travel through the outer circuit. This is a very simple working of solar cell. You can see the yellow lines. The yellow lines give you a clear idea of path of electrons. Sunlight gives the photons. These energy of photons is absorbed by electrons. With the help of electrons, the electron jumps from cross the barrier n-type to p-type semiconductor, and then they goes by external circuitry to n-type semiconductor once again. And in this way, the light energy is converted into electrical energy. Okay, so this is once again the schematics showing you how the solar cell work. As far as the solar cells are concerned, there are some critical conditions are there which should have to take into mind. One condition is the band gap, because it affect on the solar cell performance. This solar cell performance is measured in terms of efficiency. The efficiency is the formula of efficiency is open circuit voltage multiplied by short circuit current multiplied by fill factor divided by input power, whatever we are using. And this open circuit voltage and the short circuit current, they are depend on two different parameters. Like open circuit voltage is depend on band gap of the material, and the short circuit current is depend on the absorbed photon. So if you have to increase one, then obviously there will be a decrease in other parameters. So it is like a very critical thing to balance all these parameters. If you have to decrease band gap, then you can absorb the more spectrum of light, but at the same time you are going to sacrifice the output voltage. So you have to keep in mind to increase VOC as well as ISC. These are some of the materials which are used to construct the solar cell, like gallium, silicon. Silicon was the first one material used to construct the modern type of solar cell, we can say. Then gallium arsenide, CDT, CDS, CDSC. So there are a number of materials are using. Which are the advanced materials we will discuss later on. So band gap of the solar cell, or the material used for solar cell, should be in between 1 to 2 electron volt, because this is the visible, this is the reason where we can increase the efficiency. Okay, as far as the generation of solar cell concern, we can, for our understanding, we can categorize this generation in three parts. Like first generation, which is mainly consist of silicon type of material. This kind of solar cells are called as a thick solar cell or thick film solar cell. because the silicon have low absorption coefficient, and because of that we have to increase the thickness of silicon layer in the range of 200 to 600 micrometer thick, and they are highly efficient. But the problem associated with the first generation type of solar cell is the high cost. Because of that, the cost in India, we cannot use solar cell everywhere. We have plenty of sunlight. Just few days we does not experience sunlight, even though they are even though we have around 360 or 365 days of sunlight in India, but the use of solar cell is limited because of that issue. The first everywhere we are using silicon type of solar cell, but they have highly costly. So to reduce the cost, the scientist was trying to build a new type of material, that is, we can say an advanced material, to construct solar cell by using materials apart from silicon. And they discovered number of materials like amorphous silicon. By using that amorphous silicon, we can reduce the cost. Or another material like CDT or CIGS or CZTS. These kind of materials we can use to construct solar cell. These materials, or using these materials, the solar cell form is nothing, is we called as a second generation thin film solar cell, because these materials have high absorption coefficient. That's why very thin layer of them is sufficient to absorb solar light to convert into electricity. That's why this type of solar cell is called as a thin film solar cell. The beauty of this thin film solar cell is a lower cost, but the problem associated with this second generation solar cell is a lower efficiency. That's why this is not popularized. Recently, there is another third type of generation is right now at the laboratory level or research level. This is the hybrid type of solar cell, which consists first and second generation, as well as another material like perovskite or quantum dot sensitized solar cell or dye sensitized solar cell. And these are this is the third generation hybrid solar cell, which have highly efficient and maybe a lower cost. So, but unfortunately, this is not in the market right now. But in coming year, the total solar industry will be covered by this third generation hybrid solar cell. Hope so. Now, we'll just go through what is the first, second, and third generation solar cell. First generation solar cell, I already told that this is realized on silicon, mainly N-type silicon and P-type silicon or semiconductors. The limit efficiency of this first generation solar cell is about 31%. Right now, we can achieve about 90% efficiency using this silicon. The best solar cell in the market, which is given by Sun Power company, having efficiency about 22%. But the issue related with this is the higher cost and a lower payback time. The second generation solar cell, which is made up of CDT, CIGS, CZTS. CIGS means copper, indium, gallium, and sulfur or selenium. These four materials are combined together to form this type of material. The share of this second generation solar cell in total solar market is about 0.5%. So you can understand that it is a very low, what we can say, exposed material in solar cell industry. But it is a new material. The process is very cost effective and efficient, and it is used just 1% of expensive semiconductors compared to first generation. So you can see this is very low cost material. The highest efficiency as far as the CIGS is concerned is 11% right now in available in the market. Although the CIGS type of solar cell was demonstrated 20% efficiency, but right now there are so many people are working on that material, even though in CDT also. CZTS, this is actually showing efficiency 12% in laboratory, and in real case it's showing 9% of efficiency. So CDT or CIGS or CZTS, we can see these as an advanced material as far as the solar cell industry is concerned. This is the third generation multi-junction solar cells. Recently, a lot of research work is going on that third type of solar cell or multi-junction type of solar cell, which consists, you can see in the figure also, there are multiple layers. Each layer have his own work. He will contribute into the solar cell efficiency. That's why the predicted or theoretical efficiency of this type of generation, this type of solar cell is predicted from 40 to 43%. It is huge, we can say. Although the laboratory level, the efficiency achieved by this multi-junction solar cell is about 30%, which is greater than the theoretical efficiency of first generation solar cell. So you can see that's why we can say the material using in third generation solar cell are the advanced materials, because they have superior performance, they have novelty. That's why we consider these as an advanced materials. Okay. As far as the okay, I'm just keeping this because of time constraint. In coming year, you can see these kind of flexible solar cells, also printable solar cells. So you can use this kind of solar cells on your floor, or sorry, in your roofs of your home, to decorate as well as to produce electricity by using sunlight. As far as the solar cell efficiency is concerned, the record-breaking cell, which was fabricated in 2014, gives 46%. Right now, it's more than that. The third generation solar cell was showing about 35% efficiency, as compared to the first solar cell was developed in Bell Laboratory, having efficiency about 6%. So you can see within this last 60 or 70 years, we can achieve a greater in laboratory level of efficiency, but that is not like implemented in actual market. Actual market is based on silicon type of first generation type of solar cell. So these are the top 10 photovoltaic cell producers. The top 10 produce 53% of total produced world produce total production of solar cell in world. There are some companies like Q Cells or Solar World from Germany. Then some companies from Japan, China, Taiwan. So they are top 10 companies, we can say, they are manufacturing solar cell. But unfortunately, we are not in the picture. We have almost 360 days of sunlight, but unfortunately, there is no any company who is producing solar cell which is compatible with that, with this kind of international companies or worldwide. There are a lot of scope and hope so in near future we will not assemble. Right now, India is assembling country. We are imported some parts and we assemble and we can sell out here. But in near future, in India, there may be some companies who manufacture, we can fabricate efficient type of solar cell. Okay, now move to the next one. There are some methods to prepare the solar cell materials, like physical method and chemical method. Physical methods contain sputtering, evaporation, pulse laser deposition methods. In chemical, there are a number of other methods like hot injections, hydrosolvothermal, ball peeling, and all these materials. Actually, I'm just demonstrating how to construct solar cell by using one material. This work was published in 2014. This work was done in Chennai National University. So just to give an idea how the solar cells are fabricated, that's why I'm giving this an example. To fabricate solar cell, we have to prepare the nanocrystalline powder. I'm saying the chemical method. The solar cell manufacturing by chemical method. So first of all, we have to prepare nanocrystalline powder by using number of chemical methods. Then using this nanocrystalline powder, you have to deposit thin film. Then you have to anneal this thin film. That is nothing but a sulfurization step. And then by doing some backhand process, you can fabricate the solar cell. This is a schematic presentation how the solar cell can fabricate it. So first of all, we have to prepare the CZTS nanoparticles by using number of chemical methods. Then just coat this material, CZTS type of nanomaterials. You can take another type. Instead of CZTS, you can use CIGS or perovskite type of materials. CZTS, I'm using here CZTS because I work on that material. You can deposit CZTS material on substrate by using Dr. Blade method or other methods which are available. Then you can see the SEM graph, how the nanoparticles was deposited on the this substrate. But it is not effective for solar cell conversion, because for solar cell conversion, there are some requirements, like there should be a grains having size more than 1 micrometers or like this. And to develop the grains from the nanometals, we have to anneal. this thin films. So we sulfurized or anneal by using furnace. And then in fifth and sixth figure, you can see how the solar cell can produce. In third figure, you can see a very small particles, that is we know called as a nanoparticles of that CZTS. And in fifth figure, after annealing, you can see the development of nanograins by using these nanoparticles, and then you can deposit backhand processes, backhand chemicals to produce a solar cells. We can see here the fabrication process to develop the solar cell, to fabricate the solar cell. First of all, we required a substrate. The substrate may be a glass on which you have to deposit one special kind of substrate, like here we used molybdenum, because we have to anneal all the setups more than 400 degrees Celsius, and our soda lime glass will not sustain in that harsh environment. That's why we use moly as a back contact, because it should be stable in harsh environment, on which we can deposit CZTS, or people can use deposit CIGS material or perovskite material, which is p-type semiconductor obviously, which can be deposited by physical methods or chemical methods, and it act as an absorber layer having thickness about 1 or 2 micrometers. Lower thickness is okay because they have high absorption coefficient, on which we have to deposit n-type semiconductors. This n-type semiconductor may be a CDS. We have to deposit very thin layer of CDS. Many times what happens, this thin CDS having size about 100 nanometers is not sufficient to cover total CZTS. That's why to prevent the leakage, we deposit aluminum doped zinc oxide, which is we can say TCO, over the CDS, and on which we can use the ITO layer. So this is the structure of solar cell, how the solar cell can looks like. It contains soda lime glass on which molybdenum is deposited, on which our main layer, which is we can say a p-type semiconductor is deposited, on which a n-type semiconductor, a thin layer of n-type semiconductor is deposited, on which a TCO is deposited, and then finally we will get the solar cell, very small solar cell having size 1 to 2 micrometers. And when we combine the solar cells in series and parallel combinations, then we will get the solar panels and then photovoltaic assembly and all these things. So this is a schematic diagram. This is a SEM diagram of CZTS and CZTS SE type of solar cell. You can clearly see the molybdenum or moly layer over which CZTS type of grains was developed or deposited, on which a very small layer of CDS was deposited, and where you can see the backend processor processes or TCO and ITO was deposited over EH. So I will show another figure. Here you can see clearly how the solar cell looks. It contains the layer, moly layer, over which the good quality of grains was deposited, having size about 1 micrometers. It's and on which yellow colors layer you can see this is the n-type semiconductor, which is nothing but the CDS, and over which a zinc oxide or aluminum doped zinc oxide was deposited. And this is the simple structure of solar cell, how the solar cell looks like. And this solar cell can be used in numerous ways. As Dr. Srivastava told you, the use of solar cell in visual process case, in that case also you can use this kind of solar cell, or even though in common case or conventional or traditional solar cell, you are using this kind of solar cells to convert sunlight into electrical energy. Okay. So I'm talking about the advanced materials used in solar cell. There are 2 or 3 materials. More than that, there are another materials also, but because of time constraint, I'm just touching here 2 or 3 materials. First one is the CZTS. This is the advanced material used to fabricate solar cell. CZTS is abbreviation of copper, zinc, tin, and sulfur. It is a quaternary compound semiconductor having direct band gap about 1.4 to 1.5 electron volt. It is high absorption coefficient. That's why a thin layer of CZTS is sufficient to convert sunlight into electricity. It is similar material property like CIGS, but it has an abundance in nature. It's like copper, zinc, and tin and sulfur. They are abundance in nature. So obviously it is a low cost material, as well as it is non-toxic, and it has a good electrical conductivity. And as far as all other advanced materials concerned, it is good, easy in production, as well as lower in cost. Theoretical photo conversion efficiency of CZTS is about 32%, but unfortunately, it is not achieved at it. The highest efficiency using CZTS type of material is recorded as 9 to 12% at laboratory scale. Now, the second advanced material, as far as the solar cell is concerned, is the CIGS. CIGS means copper, indium, gallium, and selenium. It is also a quaternary compound semiconductor having a direct band gap in the range of 1 to 1.7 electron volt. It is also high absorption coefficient as like the CZTS, but it is a best known metal as far as the thin film technology is concerned. That's why people are working on CIGS to form actual solar cell which can be used in market or at consumer level. It is easy in production, and theoretical photo conversion efficiency is around 30 to 32%. As far as the today's scenario is concerned, the solar cell fabricated using CIGS type of material is achieved around 14% of PC, photo conversion efficiency. Another advanced material used in solar cell technology or solar cell fabrication is perovskite. So you can see a lot of research group all over the world are working in this area on this material because solar cell efficiency of devices using perovskite have increased 3.8% in 2009 to 20.25% in 2020. Recently, some groups in Japan also reported 28% of efficiency by using perovskite and CIGS type of tandem solar cell. So you can see what is the how the advanced materials are. Advanced materials are the materials which gives enhanced property. In 2009, this material shows just a 4% efficiency, and right now it shows around 25 or more than 25% of efficiency. So within 10 years, this is like a huge increments, and maybe in coming year it's maybe a record break material used in solar cell, we can say. So that's why perovskite is considered as an advanced material in material science or in science and technology field. It is a single junction, remember that 25% efficiency for single junction architecture. For tandem, if you combine silicon as well as perovskite, then you can achieve 30% of efficiency, which is exceeding the maximum efficiency of single junction silicon solar cell. So that's why perovskite is used in right now used in laboratory level of solar cell fabrication process. Perovskite solar cell are therefore currently the fastest advancing solar technology with the potential of achieving even higher efficiency and very low production cost. And which may be commercially, perovskite solar cell have become commercially attractive. As well as the beauty of perovskite, you can deposit colorful solar cell by using perovskites. Okay, now within if I have time, can you give me more 10 minutes, sir, so that I can?
Sure, sir.
Okay, thank you. So I will discuss the, as far as the solar cell is concerned, traditional solar cells are used to convert the sunlight into electrical energy, and this electrical energy can be used in home or industries or everywhere, you can see that. But as far as the advanced technology is concerned, this solar cell can be used in another area, that is nothing but a photo simulation, as Dr. Shashi Bhushan Srivastava already told you. So I'm just going into that area. We can use solar cell in photo stimulation also. Before that, what is photo stimulation? We will see. Photo stimulation is the use of light to artificially activated biological compound like cells or tissues, even the whole organisms. So by using light, we can activate the biological components as like our eyes. And in the long run, photo stimulation has a potential for use in different type of therapy. There are a number of some therapy was discussed by Dr. Shashi Bhushan Srivastava. Additionally, photostimulation may be used for mapping of neuronal connections between different areas of brains. This is a very simple schematic how the photostimulations will work. This is just a solar cell which convert light into electrical signal, but this electrical signal can be given into the biological component. This is nothing but a biointerface. We can connecting our solar cell to biological component, which is we consider it as a bio interface or biological applications of solar cells. So the quantum, the whatever the electrical signals are produced by the solar cells is given to the biological components as an stimuli for further what we can say applications. How the further applications will be achieved, we will see in next next few slides. Okay, so this is a new area as far as the solar cell is concerned, biological field or biological applications of solar cell. This can be this can be termed as neural prosthetics, which is a series of devices that can be substitute a motor or sensory or cognitive modality that might have been damaged or result of injury or disease by replacing or missing biological functional. Already Shashi Bhushan Srivastava discussed about the visual type of these biological applications of solar cell. There are another one, auditory or motor, and even though this can be used in pain relief also. Okay, so just one or two slides we will discuss. We can use our solar cell in our eyes also. Here already told you I will discuss Shashi Bhushan Srivastava, so I'm not going into detail. Actually, I work with Coach Laboratory under the guidance of Dr. Siddharth Nejamaglu, and also in association with Dr. Shashi in this material. That's why I'm just going into I'm discussing this part. I'm not going into detail. We can use advanced materials for biointerface. Some inorganic semiconductors we can use, or some organic semiconductors are used, like silicon, ZNO, CZTS. These are the conventional materials, but these conventional materials are right now using for biointerface. That's why they become some advanced materials. I already told that the conventional materials can be considered as advanced materials if they are using for novel purpose, if they are using for non-conventional, non-traditional purposes. Okay, as far as these inorganic or organic semiconductors are concerned, like silicon or zinc oxide or CZTS or perovskite or carbon nanoparticles, they are using to convert light into electricity. But here, in this case, they are using to stimulate the biological components. That's why these materials are now called as an advanced material. Advanced material as far as the biological or interface section is concerned, biointerface science is concerned. Okay, so there are number of materials. People are working on that materials, but there are another materials maybe they exist in nature who can replace this material in good efficiency. Okay, I'm not going into detail. Already Shashi Bhushan Srivastava told you all this operating mechanism, how the solar cell can be used in biological electrolyte media. Just one difference is there. In case of conventional solar cell, we are using the last one is the aluminum contact, which can be used for our electrical passage of electrons. But in this case, instead of aluminum, we use here biological electrolyte media to give a stimuli by using the sunlight. So this is just one difference between the conventional type of solar cell and this new area of solar cell is concerned. Okay, so these are the zinc oxide. I work on that zinc. My contribution in that area is the zinc oxide nano wires, which was interfaced for the photoelectrodes. Already in last lecture we discussed this capacitive type of charging and discharging. We used the zinc oxide nano rods on which we deposited P3ST and then PCBM. The solar cell was very simple. The construction of solar cell was very simple. It consists the substrate on which we deposited zinc oxide nano rods, on which we deposited P3ST, and this P3ST is followed by the PCBM layer. And this three layer assembly we called as an active layer. And if we tested this three layer activity for biointerface, then it gives a good kind of current, about 1.2 nanoampere to 3.1 nanoampere. Deposition of 3 layer, 6 layer and 10 layers of P3ST PCBM over the zinc oxide nanorods gives a good kind of shows the good kind of efficiency. I'm not going into detail here, or I'm not discussing all the details because the results are not published yet. This is a good, what we can say, uh, research as far as the zinc oxide are concerned. Recently, people's already used zinc oxide for quantum dot or dye sensitized solar cell, but this is a new area. We can use these zinc oxide nanorods for photo stimulation purpose also. That's why right now the zinc oxide becomes an advanced material. Okay. As far as the photo simulation is concerned, the photo simulation can be used to get heart attack or cardiac arrest recovery. So this is another good area where we can use our solar cell. Scientists at the University of Bonn, Germany, have succeeded in altering cardiac muscle cells to make them controllable with a light, and then causing condition which genetically modified in the mice. They work hold promise for enabling heart attack recovery. So actually, this is a very interesting study where the solar cell can be used to recover from heart attack, from cardiac arrest. The researcher genetically modified mice to make their heart muscles express to some proteins that function as both light ray sensors as well as ion channel in the cell membrane. When stimulated with the blue light, the channel opens, the positive ion flows into the cells, and this causes a change in a cell membrane pressure, which stimulate cardiac muscle cells to contract. What a great invention, we can say. So by using this is a very what we can say advanced thinking. Actually, a small solar cell can be used in different areas also. Some peoples like Sedat Nejamaglu, like peoples are working to replace our eye system by using solar cell. Some scientists from Germany, they are trying to use this solar cell uh, to increase our life, like to get a heart, like to recover heart from the cardiac arrest. So this is the beauty of what we can say science and technology. So day by day we are using these materials to enrich our lifestyle, or as well as in biological media also. This allowed the okay, I'm not going into discuss all these slides, we already discussed here. So this is a recent actually discovery or recent research. So I will skip because of time constraint. I skip all this part. Now this solar cell can be this photo stimulation of solar cell can be used in another different areas, like to increase the hair loss. You can use photo stimulation or you can use solar cell. Even though solar cell can be used in multiple, allows the photo stimulation of multiple neurons, there are already some applications are available. Some peoples are working on specific LED based red light photo stimulation. These are one kind of solar cell which is used to improve overall sperm function and reproductive performance in both, or in any other animals. You can use these kind of things. Also, these photo cells can be used in ECG amplifiers as well. So these are the some of applications of solar cell materials in the current scenario. With this, I thank you all. Thank you organizers giving me a time. Thanks all. So here I will complete my discussion talk. Now the session will be open for discussion if organizer permit us. Thank you.
Thank you very much, sir. Really, it's an amazing talk. From the audience, we have gained a lot of knowledge.
Thank you.
With your permission, I will ask few basic questions.
Yes, yes.
So, what is the optimum band gap semiconductor is required for solar cell?
One generally 2 electron volt, in between
So,
1 to 2 electron volt.
1 to 2 electrons. Okay, sir.
Yes.
And another question, that metals are already rich in electrons. Why we can't use that?
Why?
Why you can't use the metals?
Okay. So actually, long back, peoples are using that materials, but you know that there is another factor called as a work function. So electrons must be come out from that metals, and work function of the metals is not that much like sensitive to the visible light. That's why metals are not used in solar cell fabrications. So we have to reliable on semiconductors.
And efficiency point of view, a thin
Yes.
film or a single crystals, which one you will prefer?
As far as today's scenario is concerned, the peoples are like we are using single crystalline silicon solar cell as far as the efficiency is concerned.
Okay.
But in current, like in future, I already told you, in future we have to like focus on this one multi-junction type of solar cell to increase efficiency and their wide applications, because silicon solar cell has lot of limitations, cost if point of view or their availability point of view. So, but as far as the current scenario is concerned, we are on reliable on single crystalline silicon cell solar cell. But in future, we have to go for this one hybrid type of solar cell.
Okay, sir. Thank you very much.
Thank you,
Your
sir.
talk was really nice, and
Thank you, sir.
audience are telling that's a really nice session for both the speakers.
Okay, thank you.
So thank you, Shashi Bhushan Srivastava sir, and as well as Vanakar sir. And now I request for Dr. Ramanna to conduct the vote of thanks.
Very good afternoon to all present over here. It gives me an immense pleasure to deliver the vote of thanks for this event to all dignitaries assembled here. Firstly, I would like to thank our distinguished speaker, Dr. Shashi Bhushan Srivastav, ERC postdoctoral fellow, KOC University, Istanbul, Turkey, for making excellent presentations on the topic of photomodulation of neuronal activity by organic polymer-based biointerfaces, and making this seminar very interesting and meaningful. Thank you, sir. I must mention our deep sense of gratitude for Dr. Sharadrao Anandrao Vanarkar, Assistant Professor, Department of Physics, Karmir Arts, Science, Commerce and Education College, Kolhapur, for his wonderful explanation about advanced materials and solar cell applications. Thank you, sir. I would like to express our gratitude our principal, Professor U.R. Rajput, KLE's BK College Chikodi, for his support and encourage for conducting virtual conference. Thank you, sir. I am happy to express vote of thanks our HOD, convener, organizing secretaries, and staff member of Physics Department, KLE's BK College Chikodi, who have made this conference a grand success. I would like to thank faculties of chemistry department for their technical support to conduct virtual conference very smoothly. I would like to thank all the participants for making this conference a great success. And finally, thank you one and all.
Thank you, Ramana sir. So for the participants' point of view, so feedback link we have shared in a chat box and even in a YouTube comment box. So please fill the feedback link and for your certificate. So now meeting is over. So please leave the group.